Study Unit 6, Lecture 1. So Study Unit 6 continues with AC-DC converters and specifically focuses on what are called naturally commutating AC-DC converters. Study Unit 5 focused on uncontrolled rectifiers and converters, whereas Study Unit 6 will focus on half-controlled and controlled AC-DC converters. So the converter, or rather rectifier circuits from the previous study unit made heavy use of transformers and diodes to do the AC to DC conversion. The converters in this study unit make use of active silicon devices such as thyristors to perform a switching action. These types of converters are called naturally commutating controlled converters because there is once again no external circuitry which controls the commutation. Instead, the control, or rather the switching interval, is determined by the periodicity and the phase of the input sine wave. The sinusoid coming from the input will be used and passed through other networks to determine whether the active devices are turned on or not. In this way, the source signal is responsible for the commutation of the switching network which does the conversion. Once again, the networks which are characterized and considered in this study unit will be characterized by the ripple or harmonic factor, which is the square root of the form factor squared minus 1. And once again, this metric will be used to sort of evaluate the quality of the AC to DC conversion that's taken place. So shown here is figure 12.1 from the reference text, and it shows 4 different AC to DC converter circuits. These circuits all produce a continuous voltage with variable output current, and what sets them apart is how the conversion bridge has been built. So they all use a combination of thyristors and diodes. So for example, circuit A here has 4 thyristor devices, circuit C here has 2 thyristors and 2 diodes, as does D, and circuit B has 2 thyristors and a single diode, but makes use of a transformer that is center tapped to reduce the number of active devices. So in terms of the output, these circuits are pretty much all identical. Where they would differ is in the types of design choices which would need to be made when designing these types of circuits in terms of cost, power dissipation, and so on. These types of considerations would determine how viable would it be to use 4 thyristors. It might only be viable to use 2 thyristors and 2 diodes. So to control the DC load, or the power which is delivered to the load, the switching angle alpha is varied to determine how much energy is delivered to the load from the source. For these examples here, the loads are all RL loads. In other words, there is an inductive and a resistive element in the load only. So for these types of loads, the output voltage is the mean output current multiplied by R, and this is given by 1 over pi multiplied by the integral from alpha to pi multiplied by the input source, and this is equal to root 2 over pi multiplied the input voltage multiplied by 1 over cos alpha, where alpha is the angle at which switching will occur. What's important to note here is that this output voltage is only a function of alpha and not the load. To get current, the output voltage is simply divided by the resistance R, and you get a similar expression kept with R in the denominator. And here the output current is determined by alpha, the switching angle, and the resistance in the load. Alpha is also sometimes referred to as the delay angle at which switching occurs. Finally, the RMS voltage at the output is V multiplied by the square root of pi minus alpha plus a half sine 2 alpha over pi. This half sine 2 alpha comes from a half angle formula from this cos alpha over here. So all the circuits shown here have 2 operating modes with respect to the output current, and that is whether the output current is discontinuous or continuous in the load. So for the case of discontinuous current, the delay angle alpha is less than pi, and beta minus alpha is also less than pi. For a continuous load current, alpha is less than theta, and beta minus alpha is larger than pi. So what this means is that the load current will be discontinuous, where the delay angle alpha is less than pi, which will be 1/2 cycle, and the extinction angle beta minus alpha is less than pi. In other words, the current will conduct, or rather the current for the load will flow for less than 1/2 cycle of the periodic sinusoidal input. For continuous load currents, alpha is less than the conduction angle, and beta minus alpha is larger than pi. In other words, the period through which conduction takes place is longer than a half cycle, so current is able to conduct from one half cycle and into the next before the extinction angle comes into play. What this means in practice is that depending on the values of alpha and beta, the output current waveform characteristic will change depending on whether the delay angle and the extinction angle are larger or smaller than pi. Or more simply, depending on whether the current is operating in the discontinuous or continuous mode, the output current will have a different characteristic. For all the circuits shown here, the output characteristics are the same, but the conduction paths are different depending on the configuration of the AC source and the diodes and thyristors. So shown here in this graphic is the output current as a function of omega t, or the angle of the input, and also shown here for the different circuits A, B, C, and D are the different conduction paths during this conduction cycle. For all these circuits there will be some critical inductor value where above or below a certain value the current will either be discontinuous or continuous. In other words, this is the inductor value that is required to prevent the output current from falling to zero. So this critical load inductance is a function of not only the frequency and the load resistance, but also the various conduction delay angles present in the switching circuit. So a generalized form of the critical inductance is critical inductance multiplied by the frequency divided by the load resistance is equal to the conduction angle minus the delay angle minus pi over 2 plus this value over here. This expression over here relates the two angles to each other. So for alpha less than theta, this whole term will simplify to simply arcsine times 1 plus cos alpha over pi. So to get the critical inductance, this value for theta needs to be worked out, substitute back into here, and then for whatever the delay angle is, alpha, then the critical inductance can be determined. If alpha is larger than theta, then alpha equal to theta is substituted into the generalized form for the critical inductance and simplifies to minus pi over 2 plus alpha plus sine alpha plus pi cos alpha over 1 plus cos alpha. A final note on this circuit type is that if voltage inversion is required at the output, then diodes cannot be used because a diode will not allow the output to go negative. Shown in this diagram is a single phase, full wave, half controlled circuit with a load which has both inductor and resistor properties as well as a back EMF. So as with many circuits which have a back EMF, the supply only starts to conduct current into the load once the supply voltage exceeds that of the back EMF present in the load. And this angle, alpha hat, is determined by this expression here, arcsine of E, where E is the back EMF, divided by root 2 of V, which is the input voltage. Graphically, this is the point where the input sinusoid exceeds the back EMF. Like most rectifiers, the output voltage is simply the integral of the input. So for this example, the output voltage is V out equal to 1 over pi, multiplied by the integral from alpha to pi of the input signal, and this simplifies to the familiar root 2 over pi multiplied by V multiplied by 1 plus cos alpha. To get the output current, or the average output current, it is simply the difference between the output voltage minus the back EMF divided by the load resistance. And this is root 2 divided by pi multiplied by V over R multiplied by 1 plus cos alpha minus pi sine of alpha hat. The time domain solution for the output current depends on omega t and whether it is larger or smaller than alpha. Applying Kirchhoff's voltage law to this loop over here allows for the output current to be characterized in the time domain. So by Kirchhoff's voltage law, the sum of the voltages at this node must equal the sum of the voltages in this branch over here, which is simply root 2 V sine omega t, which is the input signal, is equal to the voltage over each element. So for the resistor, it's simply the resistance multiplied by the current. For the inductor, it is the change in current with time plus whatever the back EMF is. So solving for the output current as a function of time requires solving this differential equation over here. And what is assumed is what's called continuous current conduction. And for this assumption, R is equal to Z cos phi, the back EMF is root 2 V sine alpha hat, and Z is the collective impedance of both the resistive and the inductive elements, so that's the square root of r squared plus omega squared L squared, and phi is given as arctan of omega L over r. So there are two sets of solutions for this equation, one where omega t is less than pi but larger than alpha, and one where omega t is larger than pi but less than pi plus alpha. In other words, depending what this angle over here is, the delay angle of the converter, the output current function will change. To spare my handwriting, what I've done is I've posted each of the expressions depending on what omega t is. Despite how intimidating these equations look, I basically just describe this periodic output current, which is shown graphically here. So the circuit can also operate in a discontinuous manner, and there are two conditions which predicate which type of discontinuous operation happens. So in the first, the current is forced to zero before the load is allowed to freewheel, and this happens when the back EMF exceeds the instantaneous source voltage. The second discontinuous condition is when the current is forced to zero while the load is busy freewheeling, in other words, when it is not drawing current from the source. The textbook goes into quite a lot of mathematical detail about the two different discontinuous modes, but it is perhaps easier to show graphically what is happening when the circuit is operating in this manner. So shown here in the first circuit is the first condition, where the current is being forced to zero before load freewheeling can start. So this is where the current gets driven to zero before there is any kind of output voltage provided by the back EMF. In the second case, the load current is already at zero while the load is freewheeling. In other words, there's already a back EMF present, but the output current is zero. So what's happening during this section here, when the current is being driven to zero, current is only flowing in the output loop through diode D2 and resistor T3. Eventually the load current gets driven to zero, so there is no load, or there's no current being drawn from the source, and none of the active devices is conducting. Once the current reaches angle alpha, then T1 starts to conduct, as well as D2 for the return path over here, and D4 later on through here. In the second case, because there's not this added complexity of freewheeling, or rather the current being driven to zero during freewheeling, the conduction pattern, or the switching pattern, is much simpler and follows more closely to the continuous pattern. Of course, in this mode, it is different to the previous mode because there is now no current conduction at all, not even a decreasing value between the conducting parts of the cycle. Right, and that concludes this lecture.